Okay, excellent. So let's continue now by delving into the world of robotics. And this format here is going to be a fireside chat with two people that I've just spoken to, and I'm incredibly excited for them sharing their insights with you. Our next session is called Developing the Autonomous Manipulation Skills of Robots Through Experience and Play. It's going to be a one-to-one conversation with two people that we have here, and I'm very pleased to be welcoming Neil Firth, who is the executive editor newsroom of the MIT Technology Review, as well as Martin Riedmüller, who's the control team lead at DeepMind. So ladies and gentlemen, please welcome on stage Neil and Martin.
Hello, everyone. Hi, I'm Neil, executive editor at MIT Technology Review, and we're here to talk about robotics, which is very cool. Basically, one of the coolest things you can do with AI. But my question for Martin, world-renowned expert on robotics, is: we're in this cathedral of AI wonder. I've already seen so many talks today about all the amazing things that generative AI can do. My question for you is: why are robots so rubbish?
Yeah, because robotics is hard, obviously. And there's even a scientific paradox called the Moravec paradox, which says that in AI, things that humans find difficult are easy for machines, like playing chess or Go. And things that humans find more or less easy, like driving a car or playing soccer, are actually really hard for artificial systems. And this seems to be definitely true.
All right. So tell us a bit about what is it you're trying to get robots to do? So manipulation, meaning robots picking things up, dropping things, moving things around. That's it.
So we as a group are very much motivated by seeing how humans can actually learn from a baby that basically has no or very few control over their body to a grown-up who really can do amazing things with all the body and the body being very different. And so there is something that you actually can learn from mere experience to manage a very complicated system like a body. And we are very much inspired to bring similar ideas to our robots. So it would be very nice if we can just say to the robot, like, cut the meat, and it would just take a fork and a knife and do it for us. Obviously, as you already said, this is very difficult because there are a lot of degrees of freedom involved. There's dynamics in the robot, there's uncertainties. The world is always complex if you're out of an industrial setting. Things may appear on completely different places than they have been before. So you have to solve both the perception problem and the actual control problem, and this makes the problem really challenging.
Right, okay, so maybe talk us through how you go about tackling that. So I think what you're saying is what you can't do is just program in to a robot every single possible outcome, every single possible thing they may come up against, because that would just be too vast an area to search for.
Yeah, exactly. So programming, of course, it's possible as it is done today in industrial settings, but if the situations get more complex, or imagine robots that are getting more complex, that have, for example, flexible joints, or even more joints, more degrees of freedom, then just programming that would be a massive amount, and it will be very costly. And we also see it in current industrial applications. So our dream is basically that the robot can learn all their behavior from scratch, from very simple movements up to movements that then meaningful do something like grasping an object, putting it somewhere, maybe also inserting objects. And we want to do this by a technique that is called reinforcement learning, where we only put in the goal, but the robot does use its experience to improve over it. And what's behind it is an optimization algorithm or optimization principle from dynamic programming that actually allows this robot to learn by itself.
Right. So what you're saying, you're telling the robot what you want the end goal to be, but you're not telling it how to get there. It's going to sort of find its own path by sort of trial and error, basically. And this is what was used for DeepMind's, because you're with DeepMind, AlphaGo system as well, right?
Exactly. Exactly this technique produced amazing results with Go to beat the world champion in Go, and later on also to learn the whole game from scratch by just playing against itself. This is the technique. The difference to why we not just take the algorithm from AlphaGo and put it to robots is that AlphaGo didn't care particularly about data efficiency. All the games can be played in simulation, so you have tons of games that you can play. Which is probably worth a couple of thousands of years. If you would apply the same learning algorithm to a robot and you say, okay, you just wait for 1,000 of years and then it can do anything that you want, probably people wouldn't be very satisfied with it. So the trick here is to really care for data efficiency and to work on methods that actually both exploit the data that is already there very carefully, and then on the other side also take care of what data to collect in order not to waste their time by repeating the same action that they already can do over and over again, but then also know when they can do it and move away and do something next so that they really build upon this knowledge.
Okay, great. I mean, we'll come back to the data points maybe if we have time, but I also want to say I'm going to try and get some audience questions in towards the end, so just be thinking about what you want to ask in a few minutes' time. Talk to me a bit more about the children, the human brain, because neural networks were loosely originally based on the way we think the brain processes information. And you said you sort of used the idea of play and the way children learn things to sort of inspire the way your work happens. Tell us a bit more about that.
And so the idea, as I said, we really want to make the robot collect its own experience and do this in a meaningful way. So one way to do this is to look how children do this. And if you watch babies, then at the beginning they mainly do some random movements, but after some time they really go after objects, for example. They really enjoy pushing objects off the table and have fun when they can make their parents to be tools that they can use to bring the stuff back again, so they understand what their interactions mean. And we took inspiration from that and came up with a learning setup where our agent actually not only goes for the final goal, but has a lot of rewards that it sees, a lot of incentives to do other stuff before it finally can do the main tasks. And therefore, by, for example, being rewarded for touching objects, it will learn how to kind of move the hand in a certain direction until, for example, it hits the table, and then it has learned how to stretch, for example. And then when we reward this, then over and over it detects different objects. It also sees that objects moves. Then we also reward it for if its vision system detects something that, for example, the color channel shifts the mean from left to right, and then it's also rewarded. And by all that, it starts to being interested in kind of changing its environment by using its own body. And therefore, seamlessly, like from the random movements at the beginning, it more and more does something that changes the environment deliberately, and then uses the skills to finally, for example, grasp an object and stacks it on another object deliberately. And once we have that, then, for example, it's not so far from picking and placing that is usually programmed in robots, that you can then learn, for example, also to insert something somewhere, where then basically bringing an object to a certain position is not so difficult, but then understanding how to actually use the forces to put an object into a hole is a really challenging task again, but this it can learn by reinforcement learning again. So bit by bit, it gets better and better. And this is the final vision that we are currently pursuing.
Right. In terms of when you say reward, so for a child, the reward is sort of a moment of interest, something that's changed in their life. What does a reward mean for a robot in your lab?
Yeah, so at the moment, the rewards are, for example, very simple to say, okay, whenever the touch sensor senses something, then you get a reward. Then your signal goes from 0 to 1, and the optimization procedure takes care of that it collects as many ones as possible.
Right.
So these are rewards that we basically directly program into the brain of the robot. But it's very interesting that you ask if the robot can be interested in something. We are also keen to understand the general principles of interest, like something like curiosity. And one principle that is around for quite some time is whenever the robot fails to predict what happens next, then obviously something new happened. And from that, you can also generate a reward signal. So surprise gives you reward, and by having the right system, the right reward system, then also this is a way to develop more and more interesting skill in the robot.
Well, that's interesting, because that is also how children sort of learn about the world, isn't it? So sort of stick things in their mouths and eyes and learn about what you should and shouldn't do around you. Okay, so let's move on to sort of why is it important to have robots in our world that are learning for themselves about how to interact with things rather than just telling them what to do. You sort of say in industrial applications, you can say a robot arm, pick up this thing and put it there, and that's enough. Why is it important for us to have something that can interact and change with the world?
I think, first of all, of course, having a companion that you could just say things and the companion does it for you, like cleaning your house or washing the dishes. Or of course, there are dishwashers, but also kind of filling the dishwasher and putting it back will also make our life more comfortable at the end. Also helping us to serve things. So in general, the vision of having a robot that is very versatile and that can be as potent as a human is a interesting goal by itself. But even if we don't achieve this full autonomous robot, then understanding the technique, how you can learn with reinforcement learning in an arbitrary body is very interesting by itself, because there are also like control problems that have nothing to do with robotics, like, for example, controlling a fusion process or balancing a pole, the classical control theoretical challenges. These are all things that can, in principle, be done by reinforcement learning. And if we understand this general technique better and can kind of push the complexity boundary further and further, then we will have a very powerful mechanism that can control a large sort of devices, and then even the design of the devices is much more open. Currently, very many devices are just built. Robots are very rigid because then they can be controlled more easily. But if the control methods are better, then we could also probably have much more fluffy robots because the controller could, in principle, manage to control it still.
Right, okay. And in terms of, I mean, so many talks today about generative AI. In terms of that, how does that interact with your work at all, if it does? Is there a sort of...
So first of all, in generative AI, the large language models, they are trained basically by supervised learning, by having this large corpus of language where humans have produced already what they mean with a meaningful text. This doesn't necessarily exist in control, because there's nobody that has already controlled all the robots that are there to do all kinds of stuff.
Right.
So this is a completely different learning system or learning situation. On the other side, these large language models are now very good to understand daily situations, because they are described in these books and in these texts, and therefore, out of a sudden, we are enabled in robotics to have something that is nearly like common sense. So everything that we, as machine learners, brought into the approach that has to do with common sense, for example, that there are objects and that objects may fall down, this kind of knowledge is now probably built into these large language models. So the future, I see definitely that these two things will grow more and more together. In fact, I think they are just two parts of the same idea of actually finally solving AI in the true sense, to go from experience to kind of behavior, to describing this behavior in an abstract way in language, and then down to action a bit better in the real world again. So I think finally these systems, like learning control on the low level from experience and raw actions, will be connected to these higher cognitive abilities, as we see it now in large language models. And then we will have even more powerful systems that also can directly act in the real world. And then maybe even this system will inherently have a better sense of truth because they made the experience in just repeating what they have read in the text.
Right. I mean, yeah, basically, when am I going to have my robot butler who I can say what I want to happen, and it goes and makes it happen without misunderstanding me or decapitating a child? That would be good. I think we're just about time for some questions. Are there any questions out there that people want to ask? Loads of hands. Back here in the middle, please. Oh. Yeah, that lady there on the left there. Mm-hmm.
Hi, thanks. My name is Mariana van der Lande, Innovation Department. I was just curious what kind of environment you envision for training such a versatile robot. Can you elaborate?
Yeah, at the moment the environment are kind of restricted to manipulation, like we have a manipulation setup where we have a table where there are different objects, and the task is to understand what objects are there, how to grasp different objects, if you want, for example, to stack them, or if you want to put them in like an insertion task or solve an insertion task. And we also have a robot that locomote, like quadrupeds, that learn to walk in different terrains. So for example, learn to walk over steps or climb a box. So these are the typical environments. But
so they are
finally,
physical environments, right?
Sorry?
They are physical environments. You don't incorporate simulations.
They are real environments. Yeah. That's something that for example, that is also special to in particular our or my research direction, that we don't necessarily want to go via simulation, but we want to have these methods so powerful that they can be directly applied to the real world. Not because simulation or sim-to-real doesn't work in practice, I think this works very well, but really to be prepared once we have robots that are very difficult to simulate or situations that are very difficult to simulate, that we then also have a learning method that can learn directly in the real world instead to go via simulation.
Yeah, thank you.
You're welcome.
Thank you. Any more? Just here to the side. Thanks.
Thank you so much. Ante Ivancic, Rabobank. First of all, I find your line of research extremely interesting, and I'm also very curious with respect to blending LLMs with the reinforcement learning. Have you done that in the sense of, let's say, preloading those agents with a pre-trained LLM that has some contextual awareness and contextual knowledge to reduce sample inefficiency and things like that?
Yeah, so thanks for the question. So combining reinforcement learning and LLMs can happen on very different levels. So reinforcement learning can be used to kind of fine-tune large language models on language by itself to improve and to have the texts or the answers going in a certain direction. That is one thing. In robotics, also there are different uses. You can use a large language model and connect it to control. So that the agent by itself understands language commands. For example, pick a red box or push the blue button. And then immediately through this large language model, there's an intermediate representation that then can be given as a command, and then the regular reinforcement learning algorithm that learns the commands can be put onto that. There's also a kind of a bit of a different direction. If you only take from the large language models that if you have enough data and the model is big enough, then out of a sudden they generalize in a very unexpected way, in a very astonishing way. Then this could also probably happen with these raw experience and with these raw control signals. So this is also an interesting direction we are also pursuing. But I have to say that I'm a bit skeptical about this direction, whether we will ever get enough experience to do this, or whether there are intermediate steps lacking. But we see some kinds of generalization already also happening on that front. So there are different ways to combine the ideas of large language models with reinforcement learning with different goals.
Great, thank you. I'm afraid that's all we have time for in this session. So thank you so much, Martin, for joining me. It was really, really enjoyable. Thank you.
Thanks for the questions. Thank you.